Welcome back to another explainer. Today we're looking at something we literally touch every single day but probably never think twice about. We're diving into the anatomy of input devices, those fascinating physical mechanisms that actually let us command our computers. Think about it. There's this incredible translation work happening right beneath our fingertips. We're going to break all of that down and see exactly how these devices take our very human actions and turn them into digital reality.
Okay, let's dive into this with a concept I want you to keep in mind for our entire journey today. Input devices are like bridges that connect us to the computer. Without these bridges, well, a computer, no matter how insanely powerful its processing chip is completely isolated. It's stuck. It literally cannot see, hear, or feel what we want it to do.
So here's our roadmap for today. First up, translating human to machine. Second, keyboards, the typing bridge. Third, pointing, clicking, and playing. And finally, capturing sights and sounds. Let's get right into it. Section 1. Translating human to machine. Let's look at the core concept.
Before we even look at specific hardware, we got to understand what's actually happening when you press a button. An input device is just hardware that lets you provide data or instructions to the computer. Simple enough, right? But here's the secret. We provide that data in a raw format. A spoken word, a physical tap of a finger. But the computer's CPU, it doesn't understand raw format at all. So the input device actually acts as a translator. It literally converts our physical world actions into a digital language that the CPU can actually process.
Moving on to Section 2. Keyboards, the typing bridge.
It's wild to think that before modern keyboards, we actually had to give instructions to machines using paper tapes and punched paper cards. Honestly, we've come a long way. When keyboards finally did become standard, they usually had about 84 keys. But as our main typing bridge evolved, things got a lot more complex. Now, many modern Windows keyboards feature 104 or even 108 keys. They are absolutely packed with different sets of letters, numbers, functions, and characters.
And this brings us to the great hardware debate, membrane versus mechanical. Membrane keyboards have those soft keys. They're a lot quieter and, they come at a lower cost. But on the other side of the ring, we've got mechanical keyboards. These use individual switches for every single key. They're super durable and give you that incredibly satisfying clicky sound. People usually fall firmly into one camp or the other, for sure.
But hey, it's not just about the mechanics under the keys. The actual layout matters too. Most of us are completely used to the standard QWERTY layout, or maybe AZERTY, depending on where you live. But get this, there is another layout out there. The Dvorak keyboard is a totally unique layout designed specifically for faster typing speeds. It's just a brilliant piece of hardware design that optimizes finger movement, completely challenging that standard setup we just take for granted.
Let's move to and see how this builds into Section 3, pointing, clicking, and playing, navigating the digital space. So, transitioning from just typing data to actually navigating spatial movement on a screen, the humble computer mouse has heavily diversified. We've got 8 distinct types right here. Just look at the stark contrast between the older mechanical mouse, you remember, the one that used a literal rubber ball rolling on your desk, and the modern optical mouse. Today's optical mice use an LED light and a sensor for insanely precise movement, with 0 moving parts underneath. And the list goes on. Laser, wireless, wired, trackballs, ultra-fast gaming mice, and of course, the touchpad on your laptop, which lets you control everything just by sliding a finger across a flat surface.
Then we have the joystick. We mostly think of it for gaming, right? But its origins are actually military. The very first joystick was invented by C.B. Myrick at the U.S. Naval Research Laboratory. And what makes a joystick fundamentally different from a mouse is how it handles movement. With a mouse, the cursor only moves when you physically move the mouse. But with a joystick, the cursor just keeps moving continuously in whatever direction the stick is pushed as long as it's held away from its center position. Pretty cool distinction.
Now let's trace the evolution of touch input. This goes all the way back to 1955. The very first light pen, which was this highly sensitive little tube containing a photocell, was created as part of the Whirlwind project at MIT. You could point it directly at a screen to select items or draw. Fast forward to today, and that concept of direct interaction has evolved into the incredibly versatile touchscreens we literally use constantly. Instead of a specialized pen, we just use our fingers, interacting right through resistive, capacitive, infrared, or surface acoustic wave tech.
Which brings us to our final section, Section 4, capturing sights and sounds. Let's talk about digitizing the analog world.
So we've covered text and spatial navigation, but how do we digitize the super complex, messy analog world around us? Let's start with scanners. Scanners use optical technology to literally read characters or pictures from a physical piece of paper. You really have to think of it not just as a piece of hardware, but as a magical bridge that pulls physical objects straight into our digital drives. Once that physical document crosses the bridge, boom, it becomes an editable, printable, emailable digital file, whether you're using a big flatbed scanner or a dedicated photo scanner.
And this brilliantly illustrates how modern digital cameras act as input devices too, using a seamless three-step process. Gone are the days of analog film. Step 1. The camera captures the image using a digital image sensor chip. Step 2. You bridge that device to the computer, maybe a USB cable, a memory card reader, or even wirelessly. And Step 3. You just transfer those images and videos straight to the computer drive. It's literally a seamless conversion of real-world light into digital data.
Now you might be wondering, okay, how does that differ from a webcam? Well, while both capture video, webcams, whether they're built-in or external, are designed with a very specific primary objective: live, active telecommunication. They aren't just snapping photos for you to edit later on. They are the dedicated input device for video conferencing, live streaming, and social media networking in real time. Finally, we have the microphone, or just the mic. This little device has an absolutely incredible job. It reads sounds from your surroundings and rapidly, I mean instantly, converts those analog sound waves into electrical signals. We rely on this conversion every single day for voice commands, dictation, online calls, even just shouting at our smart devices to turn off the lights. It literally takes the physical vibration of the air and translates it into a language the machine understands on the spot.
Wow, we have covered a lot today. We've explored how paper tapes evolved into 108-key mechanical keyboards, how clunky rubber ball mice turned into ultra-precise optical sensors, and how MIT's light pens paved the exact way for the touchscreen glass we carry in our pockets right now. We rely entirely on these bridges to translate our human intentions into something our machines can understand. So, I want to leave you with a provocative thought here. Based on how amazingly far we've come, what do you think the next bridge between human and machine is going to look like? Think about it, keep learning, keep questioning, and I'll catch you in the next explainer.